Hey guys, this is Fraser from Thanks My Tutoring. Today we're going to be looking at mechanics and physics, specifically subtopic 2.4, which is impulse. So this is unit 2 of physics. Mechanics is a huge topic. There's a lot of subsections, there's a lot of different areas, but essentially it's to do with ideas of work and of energy and of motion. But it's a pretty difficult topic, it's quite large, and so I thought it would be good to make a video on it. So impulse, there's two ways that it's given to you in your data booklet. Either it's given to you that force is delta P, and remember P is momentum, divided by delta T. Quick reminder what P is. So just a side note, I'll do it over here. The P is mass times velocity, that's your momentum. Or they might rearrange it and say that the force times delta T is delta P. So there's two ways, and the impulse here. So impulse is essentially that change in momentum, but these are equivalent statements. So you just multiply through by delta T. So I've written down here what each one means. F is the average force. I'm just going to highlight that word average force, because we don't know anything about really instantaneous forces, but we can talk about average forces acting on the body. And this is the change in momentum, and this is sort of the change in time or time elapsed. So over what time does the motion or contact occur? So the fact that it's an average force is important, because maybe the force is changing, but overall the average size of the force was whatever, 20 newtons or whatever it is. So I've written down a question here. I mean, there isn't too much, if you understand the ideas of momentum, of this sort of, it's both the product of the mass and the velocity. So if you have no mass, you have no momentum, and if you have no velocity, you have no momentum. So if you understand that idea, and the idea that, let's say, for example, you're in a car, right, and you're going pretty fast, so your momentum is high, and then you come to stop very slowly, so you have a very small delta T. You have a very large number divided by a very small number. That's going to give you an even larger number. And so, when you brake really suddenly, you're going to feel that more than if you're going slowly and someone brakes slowly. You don't feel that as much. And that feeling, that jerk that you feel in the car when you brake, that's this force acting on you, because something has to act on you in order to slow down your momentum. Because when the car slows down, if you don't slow down, you're just going to shoot out the window, right? And so that's that seatbelt acting on you, that's slowing you down, that it's sort of dissipating your energy. But let's have a look at a question. So let's highlight a good tip in physics is you should highlight the questions, highlight the specific information, and then it gives you all the pieces of the puzzle that you can then put together. So student strikes a ball that is initially at rest. That is important information. I'm going to highlight that with blue. So its initial momentum, let's get a bit of a thicker highlighter. It's initially at 0. And it leaves the racket at a speed of 64 meters per second. The ball has a mass of, 58 grams. The contact between the ball and the racket lasts 25 milliseconds. So that's 10 to the minus 3. So, what do we know? We know its initial velocity, 0. We know its final velocity. We know its mass, and we know the time. So, why don't we go ahead and just apply the formula? So we are interested in the average force. Now note that it's the average force, right? So we can use this formula. So the average force exerted by the racket on the ball, sorry, that should be on the ball, not in the ball. So what do we know? Well, we know the force is delta P over delta T. But because the mass isn't changing, this is the same as m delta V over delta T. What's the change in velocity? It's final velocity minus initial divided by delta T. The final is 64. The initial is 0, so that's fine. And T is 25 times 10 to the minus 3. And M is 0.058. And so, as a final answer, once you put that in your calculator, and you don't make any calculator mistakes, that's 148 newtons. And because, let's see, how accurate should we be here? We should really have two significant figures, right? Because everything else is the two significant figures. So that means our final answer is 150 newtons. newtons because it's the force acting on it, and that's the average force. So hopefully that makes sense. It's the reason that the highlighting is so important is because you see all the information that you have, and over time you'll be able to go, oh, because I know this, this, and this, that means I can use this formula. So because I know the change of velocity, the mass, and the time, I can find the force acting on it. Otherwise, you don't. For example, if we didn't have the time, we would have no idea, right? So we need to know all of the variables. Slightly different, this is not to do with impulse, but it's still mechanics, just so I would add this in as well. And by the way, this isn't the whole question. The problem with physics questions is they're very long, and they usually incorporate other areas of the syllabus. So that's why physics is a particularly challenging subject, because to do the exam question, it starts off as mechanics, but then maybe it goes to waves or to something else. So they sort of weave the different parts of the syllabus together. So we're just going to cover the first 2 parts, but there's a lot more parts to it. And these are both 2 marks, so they're not loads, but it's just sort of, these are pretty easy marks because we know everything. We don't sort of have to think really hard. We just need to know which formula to apply. So average power delivered to the ball during the impact. So what I want you to think about is, what is power? I didn't write this down just because this is not exactly about impulse, but I think it's so useful to do. Power is work divided by time. So we want to know how much work has been done, and work is equivalent to sort of the energy transfer to the ball. So the ball initially, we can forget about, we can ignore gravity at this point, gravitational potential energy. Let's just focus on kinetic. How much kinetic energy so actually I'm just going to do this as change in energy over time. What's the change in energy? Well, initially it has 0 velocity, and because kinetic energy, or EK, is given by 1/2 mv squared, because v is 0, it has no kinetic energy. How much does it have at the end? Well, it has 1/2 times its mass times its velocity squared, right? And so if we can figure out how much energy did it gain and over what time, that gives us roughly the power that's delivered to the ball. So you just plug this in. That's going to be 1/2 times 0.058 times 64 squared, all divided by 25 times 10 to the minus 3. This is anywhere between 47 and, I don't know the exact value, but I think as long as it's between 47, 48 watts, I'm guessing it depends on how you round it. Let's go 4,700 watts, because it's power. It's a bit confusing that the watts and the work have the same symbol, but that's the symbol, that's the unit, and then W is the symbol for work. So hopefully this last part made sense. It's a bit extra, but it's a similar idea of thinking what's changed. Well, we know that the velocity has changed, and how can we think of power? Well, power is how much work have we done on an object, and divided by the time it took. So it's sort of the rate at which energy is supplied to an object. So hopefully that makes sense. Hopefully you learned something with impulse. I'll be making more of these videos, covering other topics, probably cover the whole of mechanics, and then move on to other topics. Let me know if you guys have specific areas of the syllabus you want to cover, and have a great day.